Hello, everybody. I am Jordi Baylina. I'm the technical lead at Polygon ZKVM. And today I want to talk a little bit about the 4844. At the end of the presentation, I will speak also about other things that we are doing in the team. But 4844, I mean, it's a really important EIP in Ethereum because actually takeoff enables and take off the data availability race. What's 4844? The 4844, the idea is the introduction of these blobs. I mean, a blob is about 128 kilobytes of data that they go directly in the consensus, so you can put this data and make it available. Okay, these blobs are going to be available only for about 18 days, but this is enough for anybody to capture that, and this is enough for Rollups to scale. As you know, in Rollups, there is two pieces that are fundamental to scale. One are the ZK proof, the validity proofs, and the other is the data availability. I mean, data availability is the important one. Okay, so here, as you know, EIP-4844 started in the last hard fork. That happens less than 2 weeks ago. Okay, and well, this is internally how it works, but this is the evolution of the last day. So since they started, of course, the first day everybody was excited and people probably was testing and so on. But here you see the quantity of information that's about 10%. It's about 10% of the capacity of the blobs. Actually, it's not the capacity, it's the standard capacity. In a block, it can be up to 6 blobs, but the price tries to stabilize at 3 blocks. Okay, so you can see that there is 3 blocks currently. This can scale maybe in the future, but this is how we are. Okay, and right now it's 10%. And I would say that not all, but most of the rollups already are using that. The ZK rollups, we are a little bit more in the delay. We will see later why, because implementing this EIP for the ZK rollups is a bit more difficult than for optimistic rollups. But yeah, probably the remaining teams in the next month or month and a half will have. But what we see here is that we are very much below the capacity. Okay, and that means that the cost is even much lower than what was expected. Right now, sending data with a blob is about 16 times cheaper than it was with the call data, with data availability. Okay, and this is, we'll see later, that this is the main driver for the cost of a transaction. So this will have a huge impact in the L2 transactions, in the cost of the fees of the user transactions. Okay, a reminder. Okay, ZK rollup, the prover is not the bottleneck. Right now, generating proofs is really cheap. Okay, and really fast. These are reminding numbers. In less than 2 minutes, in a big server, in a server that's about $1 per hour, we can generate about 10 million gas. Okay, and if you do the numbers, the cost per transaction of the proof is really low, and they can be spin it up in parallel. So if the network grows, if the network has more transactions, you can spin up more proofs, and you can generate these proofs in parallel. So prover is not a bottleneck for ZK rollups. So what's the bottleneck? Well, here are the different costs that we have. We have data availability. Of course, sending data, this is the main topic of the 4844. So putting data on chain is expensive, but there are other costs here. Sequencing, for example, well, you need to generate a transaction that actually put this data there. So there is like a kind of a fixed cost. Well, it's a variable cost because, I mean, for each blob or for each set of blobs, you need to pay the transaction fee of the transaction, and do some computations inside this transaction. So you have this sequencing part. We have the proving part. As I mentioned, prover is still a cost, but it's really low cost. Okay, and then we have the aggregation. Aggregation is very much sending the proof on chain. The cool thing of this is that this proof is quite a fixed cost. Right now we are sending 1 proof every half an hour, so this is a relatively fixed cost. And the good news is that in Polygon 2.0, all the proof of all the chains, of all the CDKs of the chain can be aggregated in a single proof. So the cost of the aggregation can be really, really low when the system, especially when the system scales, okay? Well, let me just jump here. So this is the normal ERC transfer. So this is the cost before the EIP-4844. You see that most of the cost, it's important to check not only the percentage, but also the real cost. I mean, that availability, when you are doing a ETH transfer, again, this depends on the gas price and so on, but more or less is 30 cents in an L2, which is, you see, that's most of the cost is this data availability. What happened after the EIP-4844? Well, you see that this is reduced a lot. So still is like 50% of the cost is the data availability. Sequencing can be done some things to optimize. You see this yellow thing, this is the proving cost. It's really, 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 really small. And the aggregation, again, if the system is scaled, this kind of a fixed cost, this can be reduced a lot. Okay, so here we see the huge improvement. Okay, but the good news is that EIP-4844 in the rollups will not come alone. Okay, when we are putting compression, and here, well, there is like two types of compression: normal compression, which is very much, for example, what I think most of the optimistic rollups are using. They're just doing a kind of a zip, I mean, a normal compression algorithms. You can reduce not much, maybe like 1.5x, because the data is have a very low entropy. But if you are doing stateful compression, I mean, that's you do that in a more intelligent way, you can do an extra 7x on top of that. So altogether, so you see that, well, data availability is still the cost. Here I apply also that the fact that you are compressing the fixed cost, so the fixed cost for the sequencing and aggregation is lower too. But you see here, important to see the cost, the absolute value of cost. Here we are see that with both things we are very much below a 1 cent per transaction in a ERC-20. This, I mean, this makes me feel very optimistic. I would say that with these numbers, probable validiums, most of the validiums will make no sense. I think that most of the validiums should think in really being real rollups and putting that availability on chain with this cost. And also, we are starting the EIP-4844. So this is the first iteration where there is only 3 blobs. Here we can expect that maybe, I mean, in the next hard forks, maybe this can be increased to, I don't know, 6, 10 blobs easily. And when there is full sharding, then having a 50, 100 shards is perfectly possible. So somehow the data availability, here we see a path in Ethereum, data availability will be solved, and it's not going, it should not be a limitation. Of course, this depends on the market, depends on the applications, if there are other applications that happen, but we see that the cost for data availability is going to be really, really, really low. Here this is well, you can see here the number of transactions that fits in a blob, okay? Just to give you an idea of what's in a blob, okay? So let's see what's the, well, here, of course, if you are interested, here there is, if you want to check and deep a little bit in the blobs, there is this tool about the blob scan, where you can see the blobs that are happening. There is a lot of libraries for sending blobs. There is a full tooling that's happening with the blob, with the blobs itself. Okay, so let's go to the little bit to the detail, and what's the issue, or what's the specifics of the implementing the EIP-4844 in a ZK rollup. Well, the idea is that, so this data is available, but actually is not, so it's available that anybody can recover this data, but it's not available from the smart contract perspective. When you are calling a blob, what you have access to is to a commitment of this data, kind of a hash of this data. Actually, what you have is, well, this data is this 4,048 values. These are finite field values, and this is a polynomial. These are the evaluations of a polynomial of degree 4043. Okay, and so this generates a polynomial, and the difficulty is here. Okay, so we have this polynomial where we have only the commitment, and we have a proof that actually is using the data of this blob, but we need to be sure that whatever is committed is actually what we are using in the data. So how we guarantee that the data that's committed is the actual data that's used in the prover, and we are not proving something else? Well, the trick is very much this. I'll explain you the big idea. The idea is there is a kind of Fiat-Shamir interaction protocol that's converted to a Fiat-Shamir, but the idea is that this commitment, we have, the tooling that we have in the smart contract is that we have this commitment and we can do an opening. An opening of this polynomial means that we can evaluate this polynomial in a given point, in a random point. We can choose, in the smart contract, we can choose, okay, I want to evaluate in the point 43, and then this evaluates to B of C is a number, okay? So what we do is, okay, which point are we using for evaluating? Well, what we are doing is we are doing a hash function, a Poseidon, a hash function that's very ZK friendly. So we get the blob, okay, and we hash all this function with a Poseidon hash function, and this gives us a number, okay? This is the point where we are opening. That means that if we change the data, so if the data changes, this opening point is going to be different. Okay, so what we do in the smart contract, when we are committing to, when we are sending a blob, we are also providing the hash function, this Poseidon hash function as a parameter, and we evaluate the opening of that parameter. So we have this, X and X and Y, okay? So we will have the point where we want to open and the evaluation, and we do that in the smart contract. So we know that whatever is committed, the polynomial at this point is correct. So mainly what we do in the prover, in the ZK circuit, what we do is, well, first we do the Poseidon, so we take all this data and we hash all this data. We compute this X, this evaluation point, so it should be exactly the same. X and Z are like public inputs of the circuit, so we guarantee that the data matches with the X. If it doesn't match, then the proof is not valid. We need to evaluate the polynomial, the evaluation of this polynomial with the data. We need to evaluate this evaluation. We need to evaluate Y. We need to do that in the circuit. This is the hardest part because here we are cross-field. We are working with a cross-field prime, and here we are using the barycentric formula for computing this evaluation, and then we check that, of course, this output matches with the Y. If that happens, that means that the data that we are using is correct. It is that if we change the data, of course, the evaluation is different, and if the evaluation is wrong, that means that we are using a different polynomial. Okay, so with this we guarantee that the data is the same. Okay, so but this is not all. Okay, because the other difficulty is that this data, it's a fixed length. Okay, so it has a blob has 128 kilobytes. Okay, so we need to change a little bit the recursion structure that we had in the rollup. This is the recursion structure that we have. We have batches. In each batch, actually, we prove different blocks. Okay, and each block, each transactions. But we have the basic unit of proving proving a batch, which is about 10 million gas, more or less, depending on the things. We have a first stage of compression. This is very specific to Starks, just to reduce the size of the proof. And then we have an aggregation proof. This is a recursive circuit that you can take from 2 proof, we convert to a single proof, and then 2 proof more and single proof, and we can kind of a tree, okay, and we generate a single proof. And finally, we have the final prover where we convert this Stark to a snark with, okay, so this is what we have right now. But with the prover, when we have blobs, this changes a little bit. We need to take a little bit the same structure that we had before, just to aggregate many batches so all the batches of a single block are aggregated. We have a new proof that's actually the proof that generates this a polynomial evaluation of the polynomial. Here also, in this proof, we will put all the compression, and this is already prepared for the compression and other things that can happen here, removing signatures and other things that can happen here, or even computing with the pairing, you can avoid having to do this evaluation in the smart contract. Okay, so we have this inner blob. Okay, we aggregate all them to the outer blob, so this is a proof of a blob. Actually, it's proving all the batches of the blob plus this inner blob, and then again we aggregate many blobs to have a single proof, and finally we have a star. So we go from 3 proofs to 6 proofs altogether. Okay, well this is not supposed to hear. So for this new circuit, I don't know why. Okay, for this new circuit, mainly what we're using is we're reusing the same infrastructure that we have for the batch proof. We are using the same ZK processor that we are using. We modify a little bit the arithmetic circuit just to work with this specific prime field for the evaluations. We remove some of the state machines that we don't use anymore. Okay, but the idea is that we're using the same infrastructure. Okay, so at the end we have a kind of an assembly, a ROM that's running in this ZK processor that computes this. Okay, and here is this is the barycentric function for the evaluation of polynomial. Okay, so this is one of the takeaways, the presentation. I mean, talking about 100x cost reduction is really a fact right now. EIP-4844 opens this. Data compression is the next step. Okay, so this is one important takeaway. Just to mention before ending the presentation that we are also, actually yesterday we in testnet, we're working very close with Polygon for the ZKVM, so that the node right now, we will expect a 50x performance increase. Right now it's open source, it's already running in Cardona or testnet. And yeah, and very soon we will make that official. So here the throughput of the sequencer, which was a little bit one of the bottlenecks that we had, this is going to be solved in the upcoming weeks. Okay. The other thing that we are working in the BADCOPS. BADCOPS means variable degree composite proof. This is a kind of an improvement of the prover system. The idea is, instead of working with a big monolithic proof, that's this batch proof, the idea is that this proof is a composite proof of many subproofs, and with aggregation, you can do variable size proof. So this allows us to use better the cells, the cells of the prover. So it's going to be much more improvement. And what's better, this will allow us to do variable things. So some of the limitations that we have in the type 2, that's, for example, if you are doing some edge cases like a loop of Kechags or things that you don't have enough resources in the proof to prove that. Right now we are checking that. I mean, we got this idea of ZK counters. Okay, so the idea is that if you cannot generate a ZK counter, if you cannot generate a Ketchag, then you still have a proof. So, but you prove that you cannot generate a proof. Okay, so we can do these things. But with these BADCOPS, we remove very much this idea because we can do variable size. Of course, we need to keep still the counters because the variable proof means that we need to charge. So we need to pay the prover according to the difficulty of the proof. So we need to count, but from the user perspective, they will not be limited by these counters. So that's why also these BADCOPS is important. Okay, and of course we are working a lot. I haven't talked in this presentation, but we are working a lot in the Polygon 2.0 idea, the CDKs and the aggregation layer that we presented very much. Just a word here is that all this ZK proving, all the ZK proof is fundamental for this composability between chains. I mean, we are targeting in the aggregation layer, not now, but in the next version, to have a composability between chains of less than 10 seconds in between chain. Atomic transactions, I mean, there is a full topic that we are really working hard on that. This is a little bit the roadmap that we have. Again, this is not a commitment. This is just our planning that we have, but I think is saying to share what we are doing. Right now, we're onboarding a lot of CDKs right now. We are working really hard in the 4844. Right now, we are integrating the 4844. After the 4844, very much we will start with that compression. In parallel, we have Erigon, the Erigon RPC and the Erigon sequencer that's working in parallel, and there is another team that's working in the PIL2 but COPS. Let's see if by June we have a first version of that. This is quite advanced, by the way, so we hope that this is doing good progress. And of course, the aggregation layer is the other path that we are working hard from inside Polygon. So that's very much my presentation. Thank you. We have questions.
We have 5 minutes for QA time. Does anybody have any questions? Okay.
Thank you for your presentation. Just wondering, for the aggregation layer, do you guys plan on, I guess, opening up the network to a network of provers, or what's the roadmap for, for the future of provers?
So right now, what we have is we are aggregating. So right now, what we have, and we will enable. So everything is done, but we are very much in the auditing phase. But what we will enable very soon is aggregation of the proof. The idea is that the CDKs, they can send the proof themselves, but they can also send the proof to a centralized server, and they will be aggregated with many other proof, and a single proof will generate a single proof. This is the version. This is the version 2. In the version 1 is just what we have right now is the LXLY bridge, so you can already transfer between chains, and you can transfer, okay, but you need to write. But I mean, all the chains, they need to generate their own proof. So the version 2 is this, and the version 3. This is the one that we are working really hard. I mean, it's a more complex project, but the idea here is. Let me explain you the big idea here of this aggregation layer. The idea is that another chain, in order to use the funds of a single chain, is not necessary to have the proof. Of course, you have the proof that this state is, the commitment and the proof that this state is valid, they can already use it. But if the other chain can generate the proof, they already can use the proof, because the idea is that if nobody sends the proof of the chain A, that's you're relaying, the chain B can send the proof. So they can guarantee, they have a commitment, and they guarantee that the other chain is having. So that means that a chain that's following another chain, if they can generate the proof, they can generate. Of course, this scales bad, but then if you wait for the proof and you have faster proofs, then you just don't need to follow the chain. You just can have the proof. This has it's a full topic. There is a dependency problem. A chain can depend on various chains, and then you need to solve these dependencies. This will work in it's not really a blockchain because it scales much better, but a kind of a blockchain just to coordinate these things, okay? And this blockchain also will have all the incentivation, all the economics for the proof building and all that, and and also we'll coordinate the aggregation of the proof, and we'll generate the proof with to mainnet. Okay, so this is very much the idea of the aggregation layer. It's a full topic, but this is the big idea.
Do we have more questions?
Thank you. Yeah, I had when you were showing how you build a Fiat Shamir thing. It looks only. If I read the slide correctly, it seems that you're only using the blob as the source of the Fiat Shamir.
Well, it's a summary, but
it's a summary.
But the idea is here, okay? But the idea is that the smart contract, so there is like a smart contract sends to the mean, the smart contract sends to the prover the KCG of the block. Actually, is okay. The verifier sends zit. Zit is the hash function of the data.
Right.
So you cannot. So you send the data, and here is the hash function. You send the data. So okay, you need to open to this point, and then you do the opening.
So you have to pre-commit to the blob before you get the
the commit happens in the commit happens in the smart contract. So a blob happened. You already have a data, and there is a commitment. It's a KCG commitment that's available in the block. So there is already commitment of the data. Okay. So you send this commitment to somehow to the data. So that's the idea. Actually, I mean, you are doing a step ahead, okay? Because it's, I mean, it's Fiat Shamir, okay? But the idea is, okay, because you have the data, you have the hash of the data, you know the hash of the data, okay? And this is the random opening, the random opening point, okay? So this is in the smart contract. We do this opening, so we guarantee that this opening in the smart contract matches, and we do exactly the same in the prover. So in the prover we do the hash, also the hash function, so we compute like a verifier. I mean, we are verifying this in the prover. I mean, it's verification of the blob. Okay? So this is a verifier, but it's in the prover side. Okay, so I mean, the idea is if imagine that data changes, okay, then the Fiat Shamir, the opening will change, and because so the zit and so the opening and the result of the opening is a public input of the circuit. Right. Okay. So when you are proving, so you need to guarantee that this opening that you are putting in the public input actually matches. Right. Okay. Yeah, but this is computed also in the smart contract. Okay. And and you also need to check that the opening point is the hash of the data. Gotcha. Okay. So with that, you have the hash of the data, you have the Polygon, and this is Polygon is actually passed to the batch processes. Actually, I mean, it's not. It's like many Polygons. It also contains many Polygons for the different batches. But yeah, that's more a detail. But that's the idea is this. The idea is that you need to do an opening, so you need to compute a point evaluation inside the circuit. Yeah. Okay. Cool. Yeah.
Thank you, Jordi.
Thank you very much.